welcome to part 2 of lecture 5 of ENGR 231 Engineering Statics. In this part of the lecture, we are going to look at our first calculations of moments, and here we're going to look at calculating moments in 2D planes, or for systems in 2D planes. And in particular, looking at doing this via scalar rather than vector methods. So 2D moments, scalar formation, or scalar formulation. So we saw in the previous portion of the lecture sort of some of the theory for what a moment is and what is necessary to generate it, but I thought I would go through now and actually start looking at some calculations. So the basic equation for a moment can be expressed as follows. Moment equals force times distance. Very similar to an equation you see in physics class for the calculation of torque. Now, why we use the term moments instead of torque is always something engineering statics students tend to ask. It's one of those things that torque is usually more specific, well, in engineering parlance anyway. Torque is usually something we deal with specifically when looking at rotational systems like rotational shafts, drivetrains, that sort of thing, maybe gears in some cases. Moments are more generic and more universal. You can use them for things like moment of inertia, second moment of area, first moment of area, that kind of thing. And it's a little bit more general term, and we use moments for so many different things. It's just one of those things that we refer to. As moment versus torque. So, or if you just want to think of if you want a simpler definition or a simpler explanation, well, in engineering we tend to use moments, and except when we're talking about torque. And we only tend to use torque for a handful of very specific things. So generally, I know in physics courses, especially things like high school physics, you use torque more freely than you do, or use the term torque more freely to many of the types of systems that we will apply moment to. But again, this is a engineering class, not a physics class, so we use moment for most of our work here. And that's actually for everything. In this particular course, we use moment. We don't use torque here. You do sometimes use torque in, say, mechanics and materials, which is a course most students take after engineering statics. But anyway, let me give, if I'm going to use this formula, I need to describe, put a lot of corollaries, or caveats, I should say, on this, because I can't just say, oh, you just multiply the force times the distance. Let me explain what all these things are. M is the moment, but the moment about is the magnitude of a moment about a point. A moment about a point. Magnitude of a moment about some point. And then F is not just the magnitude of the force. It is the magnitude of the force, magnitude of force perpendicular to the lever arm. Perpendicular to the lever arm. And D is the length of the lever arm. So we can do moment equals force times distance, but you have to separate out the components of the force that are perpendicular or not to the lever arm. So let's go ahead and look at some examples of this. So let's say I have a point P, or maybe a point O here. Actually, let's go ahead and do this on a coordinate plane. So we have the x and the y-axis, and we have the origin here. Then, let us say we have a point, point A, and let's say this distance is 12 inches. Distance there is 12 inches. And let us next say that I have a 10-pound force, and this has a slope of 3, 4, 5. Oop, that's going to go away. It has a slope of 5, for the hypotenuse, 4 on the vertical, and 3 on the horizontal. So I'll make this simple, do a 3, 4, 5 triangle. A 3, 4, 5 triangle. Let me just erase that. Kind of, nope, keeps trying to open the menu there. A 3, 4, 5 triangle. Okay, sorry about that. 10 pounds. So what I want to do is I want to apply moment equals force times distance, but I want the force, I don't want all of the force. I only want the component of the force that is perpendicular to that lever arm. The lever arm in this case is horizontal, and so I need to use the vertical component of this. So again, lever arm is horizontal. Therefore, need the vertical component of the moment, or of the force. I need the vertical component of the force. So really that's not too bad. The F perpendicular, I mean, you don't necessarily have to write it out this way. I normally would just bake this calculation into my main moment equation. But the force perpendicular is going to be 10 pounds times 4 over 5. That'll give me the vertical component, or just 8 pounds. And then I can just use moment about O is equal to force times distance. And that's going to be, the distance is 12 inches. Actually, I'll do it in order, 8 pounds. 8 pounds, if I can manage to write the word pounds properly, times 12 inches. And that comes to 94. 94 inch pounds. 94 inch pounds. Does that sound right? Did I math that correctly? I hope I didn't make a stupid math there. 12 times 8 is... Oh, yep. Oh my god, I am an idiot today. Oh, 96 inch pounds. Wow. 12 times 8 is 94. Jesus. Okay. Anyway, 96 inch pounds. That is our moment. And fairly straightforward. Also, direction of this. This is a counterclockwise moment. Therefore, positive. Our sign convention for moments is going to be the same sign convention we would use for, say, a traditional measure of angles in pre-cal or something like that. We have moments are counterclockwise positive and clockwise negative. So this force, if we look at it, even before we did the math on it, now when we do this with vectors, the nice thing about vectors is it does automatically give you the sign on this, the positives and negatives. But here, looking at this, usually when we do the multiplication, though, we do actually have to consider, we have to, if we're just doing a moment equals force times distance calculation, it is up to us to figure out which direction it's going and whether that's supposed to be positive or negative. So we'll see that in a more advanced application in the next example. But looking at this, this force is going to cause a tendency to rotate counterclockwise about the origin. If you look at this, again, it's going to have a tendency to rotate counterclockwise about the origin. And also, that force would cause different tendencies to rotate depending on what point we're looking at. So if I some moment about a point over here, this would actually cause a negative moment about this point right here. Or if I some moments about this point here, that would be 0 because that force would, the line of action would go right through that point if I actually gave accurate coordinates for it, etc. Okay, so let me show you all a little bit more advanced example. Let's say both the x and y component would generate a moment. In this particular case, the y component was the only one of the force was the only thing generating a moment because the x component, its line of action passed right through the point. So let's go ahead and maybe for this one I'll also show that we don't have to take things about the origin. We can take moments about any point. So actually make this nice and big. So still 2D, but a little bit more advanced. So we have our x and y axis, and let's say we have, let me just give us a couple points. Let's say we have point A, which has coordinates of 1 inch and -2 inches. And we have point B of, let's say 3 inches, comma 3 inches. And then, now let me think about what direction I want this to go. Do I want to go it this way, this way? Let's see. Basically, I want to get the components in the opposite directions. Let me think about this. That's going to be... maybe something like that. Because then... yeah, that'll work good. That'll work well. Okay, so what I'm going to do is I'm going to have a force going through B. And that force through B, let's say that's a, I don't know, let's make it a lot bigger. Let's make it 10 kips. And then if you don't recall the word kip, a kip is 1,000 pounds. A kip is 1,000 pounds. And so I then want to find the, let me give you the slopes here. Or let's actually go ahead and do this with angles. Let's say this is 30 degrees. So this is given. And we want to find the moment generated by this force about point A. About point A. So we need to then, for this it's going to be a little bit tricky, because in the previous case, so let's go ahead and write solution. Again, in the previous case, we had a situation where one of the components generated no moment because the line of action passed right through there. But let me separate this out a little bit. Let me draw this a little bit bigger. We have point A here. And up here we have we have point B. We have point B. Now, I would like to go ahead and get the dimensions on this. So I'm going to go ahead and draw a little rectangle. Just showing this like this. And I would like the dimensions on this. So from 1 inch to 3 inches, the dimension on this thing is going to be 2 inches. There is a delta x of 2 inches between these. And the reason I'm using this is that this triangle or this drawing is going to allow me to get my moment arms very easily. And then -2 to 3, that is a length of 5 inches. Now, okay, so the difficulty here is that both of these components, or both of the components of this 10 kip force, will generate moment about point A. So I have this basically a 10 cosine 30. That's going to be the x component of that. 10 cosine 30 degrees. 10 cosine 30 degrees, a horizontal force pointing there. And then vertically, the vertical component of this will be 10 sine 30 degrees. Sine 30 degrees. So again, in the previous case, the vertical component generated a moment, but the horizontal component passed through the origin, so it generated no moment. But here, both the vertical and horizontal are going to generate a moment. So, and the moment arm for the vertical component is going to be this 2-inch distance, and the moment arm for this horizontal component is going to be the 5-inch distance. So they have not only different magnitudes, but they have different moment arms. And as we'll see, they actually have different signs as well. So let's go ahead and work through this mathematically. Sum of moments about A, counterclockwise positive. I will have 10 sine of 30 degrees, that is the vertical component of this 10 kip force, times a moment arm length of 2 inches. 10 kips sine 30 degrees times 2 inches. And I gotta ask, should this be positive or negative? Well, look at the vertical component of this. It is wanting to rotate counterclockwise. And if you're having trouble, and this is something students often have trouble with, and it is kind of hard to wrap your brain around, or it can be. Imagine taking this arrow and dragging it down here. And then think about, the way I really think about this is, think about a rotating object. Think about back to physics class. If you have an object rotating in a circle, and if it wants to rotate counterclockwise, think about what its velocity vector looks like at any point in its rotation. Its velocity vector would look like this as you go around the circle. So as you go around a circle, the velocity vector is always tangent to the plane, or tangent to the circle, and if it's going to rotate counterclockwise, its velocity vectors would have to go like that. That's personally how I think about this. Now, my brain works in weird ways, so maybe I just think really weird, but whatever it is, figure out a way that you can get your thought process around this idea, or align with this idea, that, again, if you should be able to basically, given a given vector, for 2D systems, what you really need to be able to do is, you need to be able to look at a vector in relation to a point and say, is that rotating clockwise or counterclockwise? This vertical vector here, it's rotating counterclockwise at point A, so therefore it is a positive. And this is not mathematically difficult, but it's something that students often struggle with. And a common source of error is that sometimes students will confuse the idea of positive forces and positive moments. See, they'll see both of these force arrows are positive. I mean, this one's going to the right, this one's going upward. This is a positive force, this is a positive force. And so sometimes people think, oh, the force is positive, therefore the moment has to be positive. And that's very wrong. A positive force can generate a negative moment, and a negative force can generate a positive moment. And what I mean by a negative force in this context would be a force that is to the left or downward. Either of those is capable of generating a positive or a negative moment. What matters, whether a moment will be positive or negative, is the direction of the force and where it is relative to the point. So if I take this force here and I move it over here, currently it's generating a positive moment where it is, but if I drag this thing over here, now it would be rotating clockwise about point A, and it would be negative rather than positive. Okay, so I know that's a long explanation, and hopefully you can wrap your brain around that, or this is also one of those things that you just get better at with practice. Then minus 10 kips times the cosine of 30 degrees, times 5 inches. And again, the reason I did minus on this, the reason I made this term negative, was because the x component here is rotating clockwise about point A. The x component is rotating clockwise about point A. That's like a positive moment there, or positive rotation. And negative rotation, if you think about velocity vectors around that, negative rotation is clockwise, and the velocity vectors look like this. So again, one more time, this force is rotating clockwise about point A. This force is rotating clockwise about point A. And I love examples like this because one of the cool things it indicates is that a force, its individual components might actually generate moments that are in opposite directions. Its individual components will actually be, in this case, I deliberately chose the force. And you probably remembered me when I was setting this up. I was going back and forth in my head. Okay, how do I get that set up to do what I want? And yes, the vertical component here is generating a positive, while the horizontal is generating a negative. So at this point, let's just throw this in a calculator and get this over with. 10 sine 30 degrees times 2 minus 10 cosine 30 times 5. And if I manage to math that correctly, that comes to negative 33.01 kip inches. Negative 33.01 kip inches. And that's the basic idea for finding moments in scalar form. Now, interestingly enough, you could also, on this one, this is one way to do it using the component method. I prefer that if I'm doing 2D moments and simple 2D moments like that. You could also do it just without bringing it down to components. But the way you would do that for this type of problem, for example, is what you would need to do is if you have your point A here and your point B here, and the force, like this, you could drag this back, or you could do a whole bunch of trigonometry. Well, not a whole lot of trigonometry, but you could actually directly calculate that perpendicular distance along its line of action. That works as well. If you're willing to calculate the absolute perpendicular distance between the force's line of action and the point that you're taking a moment about, at that point you can just go ahead and do force times distance, and that would work out just fine. But usually that trigonometry can be a pain in the butt to work with, especially if you're doing scalar moments for 3D systems. At that point, you're doing distances in 3 directions and doing all sorts of crazy angles. And at that point, you might as well just use the components, or in 3D, usually you'll just use the cross product, which is what we'll see about in part 3 of this lecture. I don't usually do the perpendicular distance even in 2D problems, because honestly, most of the time it's just not worth wrapping your head around the trigonometry. Usually it's a lot easier just to use the perpendicular method and break the forces down into perpendicular components, or into their x and y components, and then use the x and y coordinates as perpendicular distances. All right, that'll serve as the brief introduction to scalar vectors, or scalar moments. And I think that'll do it for part 2 of the lecture here. Again, all I wanted to do is introduce the method of finding moments using scalar products. And in part 3, we will introduce the cross product and how to apply that to finding moments of a point when you're doing using vectors.